Just we're just about to get started, gentlemen. It's just my device is taking a little bit of effort to boot up. Okay, we can shut that down. Let me share my screen. Share, that's fine. Share, start the broadcast. Optimize here. Okay, and we'll start here. All right, gentlemen. So, exam one is available, right? If you have a question on the exam, you can screenshot it and send it and ask me, right? If you're stuck on the question, it just really becomes a time sensitive matter. Like as long as I see it before you submit it, then you could possibly use it. But if I just don't see it or I get back to you like hours later, then obviously you either would have finished the exam or you might have started a new one or something. So I think on Monday we were reviewing for exam one. Exam one is basically chapters 1 and 2. It's available now. I think it's due this upcoming Monday. So today we're gonna review chapter 2 as best we can. Okay, let me see. I got it here. Okay, and we want it between this and 105. Generate. We're starting for question 84. Hope everyone is doing well. I don't know. I got like a argument. I can't get rid of it. Sorry. There we go. Let me see. For the scatter plot on the right, determine which, if any of these functions, might be used as a model for the data. Let me see. It's a polynomial. Hang on. Oh, we're another name now. I mean, it could be. I'd have to dig a little bit. I guess I kept thinking, like, why does that name look so familiar? Anywho, exponential, that's not behaving like an exponential. If anything, is more so behaving like a log, right? It's polynomial, but not quadratic. Well, what's shown is like a portion of a log function. It could either be a log function or a quadratic. Which of the functions might be used as a model for the data? I think the first one, let's see. I think that's the logistic growth model. No, that's not logistic growth. Oh, it is logistic growth, yeah. Exponential polynomial, but not quadratic. It could be logistic, but that's usually not how we do logistic. It's not really behaving like an exponential because exponentials usually have like a horizontal asymptote. It starts off along that horizontal asymptote and then grows exponentially. It could be logistic, like if it was moved down some. It's not all the way logistic. It's not exponential decay, like in part B. It could be polynomial or it could be logistic. I'm torn between A and B. I'm gonna just guess and check. So I'll go with C first, and then if it's not this one, then let me see. Exponential decay. That's not exponential growth. But I'm torn. Oh, there were more options. I was like, what? I know it's not those two. I didn't even scroll. Let me change my zoom. Well, I wasted two. I didn't realize there were more options to zoom out. I was like, what? So we've ruled out exponential and we know it's not A and B. So we got one more chance. Logarithmic right there. Quadratic. It's closest to logarithmic. Let's go with that one. This is our final guess. I didn't realize we had more options. So I feel like I should draw the general shapes. It could be logistic, but it would have to be shifted down and cut off. But that's fine. I didn't realize we had. Oh, that was it. Let's do another one of those because we didn't see all the options. I think it's the same. Let me just do a few more, see if it changes. No, I just want a similar. similar. It's not changing. Okay, well, I guess if you ever see this question, it's a good chance that this is what it'll be. No, not that one, logarithmic. Okay, so I was kind of hoping that it would change, but it's not changing, so that's okay. Yeah, I didn't realize it was more options. Okay, let's go to another one. Let's go to question 6. Right here. Let's see. An initial investment, P, annual interest rate. Find the future value of the given investment where it's compounded annually, monthly, daily, continuously, and then find the doubling time from the given rates. Okay. So I'm going to try to do this one a little bit quickly, and I'm going to use my graphing calculator right here. Okay. Let me see. So if we're doing annually, monthly, daily, continuously, that means the term that's changing is our number of compoundings, which is n. All right. So we got a couple of formulas at play. Most of these are going to be covered by the compound interest formula. I think we want the future value. So let me take a quick note right here, just so that you guys can have it for reference. All right. So just for a quick reference, like for instance, if we're doing compound interest, the future amount, let me see, A of t is going to be P times 1 plus, I think it's R over N to the power of N times T, right? So that's the formula that I'm using, but with parts A, B, and C, the only thing that's changing is N, right? We should have the principal and the rate and the time, right? And we just got to put it in the right units. The only thing that's changing is N, so that's going to count as our variable. So in my graphing calculator, I'm going to put it here in the Y equals, and then just find those results quickly, or at least for the first 3. So the principal is 21,000. 1, 2, 3. Let me see if I can use my keyboard. Okay, there we go. 1 addition is quotes. I think I can hit this. Okay. So 21,000 times 1 plus the rate. So if it's 4.8%, we have to do that as a decimal. 0.048 divided. Oh, shyster. Hit the wrong button. 21,000. Okay, I guess. Let me see. Parentheses. 1 plus 0.048. Now division is M. Okay. 0.048. Our compoundings is our variable, so we're going to make that X. X is it's one of these. There it is. Okay. Let me see. So R over N. Okay, I think we're okay there. Close parentheses. Hat. Okay, parentheses. Our N is our variable, and the time. Now, if it's 15 months, we got to convert that to years. So we say 15 months divided by 12 months to get the years. 15 over 12 reduces down to, if you divide both of them by 3, you get 5 over 4. Hang on, I'm gonna turn that off now. As soon as you guys start doing that, it gets distracting. I gotta turn it off. Oh, right here. Okay. And anyway, I'm just doing 15 over 12 to convert it to years. I could just leave it as 15 over 12. That'll work too. Okay. Let me see. Multiply. Nope. R. Replicate. There it is. Times. I think the way we have it typed is fine. So I'm going to say my X, which is here. close the parentheses. So that way, the only thing that's changing is n. I think our formula looks good, so I'm gonna go back to the home. So then I'm gonna call on this function that we just typed in. Let me see. So for part A, if it's annual, that means it's applied once per year. So I'm gonna let x be 1 or let n be 1. And then it says round to the nearest cent. So 222 6747. 222 6747. Let's see how do we do for the first part. Because if we get the first part right, then the rest should flow. Triple two 6747. Yeah, that looks good. Check. Okay. The future, so if it's compounded monthly, now our n is 12. So we're just going to recall that function that we typed in. And instead of evaluating at 1, we're going to evaluate it at 12. 9590. So 222 9590. 9590. Daily would be 365. So instead of n being 12, now we let n be 365. 9848. 9848. 9848. Okay. All right. So the first three were compound interest. If it's continuous, then there's a continuous compound interest formula. I low-key, we might be able to do a trick instead of using the continuous compound interest, which we should do. I kind of want to try something. Well, here, I guess I could just do the continue. Like the trick would be, so it's like continuous compound interest is like the number of compoundings per year is always applied. So if we let n be like a really large number, it should be close enough to the compound interest formula result. I'm going to try it and see if it works. If it doesn't work, then I'll just use the compound interest formula. All right. So I just want this to be a large number. First, I'm going to try to go beyond its limits, and then I'm going to start removing digits until I can get it. Oh, let me see if I can go bigger. I didn't think it was, I thought the number was too big. Maybe this isn't working. 365, that doesn't look right. Let me try one more. 210. It should be more. Like the first one was promising, but then those last couple of ones were not. So I'm not confident in that. It should be more because usually when you do more continuous, it's going to be more interest in a year. So that number looks off. So I don't think that works. So we're going to scrap that. And what we're going to do is go to y equals, and we're going to put in the continuous compound interest formula. I'll put a note here for your reference. So for continuous compound interest, the future amount is going to be equal to, basically I do PERT, P E to the RT. So that's the formula that I'm going to be using. My principal is 21,000. So that's my P times E. The rate, so 4.8% as a decimal, 0.048 times T. Okay. Let's see something. That goes to 0. And then 1 to a power. I guess that makes sense. So if you think about the previous one, if we let that n get really large, that denominator gets really large in that first equation, that 0.048 divided by x, that term goes to 0. If that term goes to 0, then you have 1 to some power. So then that's just going to be a 1, and it collapses to the 210,000, the 21,000. All right. So that's why that wasn't working, but that's okay. So we have this one. So we're going to go ahead and evaluate this. We have the rate and the time. Wait a minute. There's no X. Oh, okay. So maybe we can just call on it. Let me see if this works. Let's go to Y2. Let's let X be like, I don't know, it doesn't matter because there's no X there. That looks promising. Yeah. And if we do several different values of X, we should get the same thing because we didn't put an X in there. Wait a minute. Okay. Let me just do the calculation here. Okay, so 21,023 times E to the power of the rate is 0.048 times the time. Oh, you know what? I don't even think we adjusted the time either, but that's okay. We'll get it here. 15 divided by 12. Okay. So we're using PERT. What's the time? I'll check the attendance. That looks better. 222, 9856. 9856 is proper. That looks right. Notice I was closer to 365, but it's still slightly more. 123, 9857. Okay, well, simple thing is we just use the PERT formula. Let me check on you. Wait a minute. Find the doubling time for the given interest rate. I think I should write this out. So if we start with 21 and we want to finish with 42, then we have to solve for T. Let me see. And I think we use the PERT formula. It's going to be 2. So let me see. Is it? Let me think about it. Give me a moment. I'm gonna take some notes here. And I think I'm gonna write it out though, because I was trying to do it here is gonna be too much. Right here. So, for instance, if we started, I forgot to charge this thing. Well, at least this is charged. I forgot to charge the pen. I charged the keyboard, the tablet. I just forgot but the pen can charge. Like honestly, when I first got it, they were like, "Oh, 15-second charge to keep it charged for like 30 minutes." Right? I think the efficiency or the effectiveness of the battery has gone down over time, but when I first got it, that's how it was advertised. Okay, so if we're doing continuous compound interest, and if we're starting with 21,000 and we want to finish with 42,000, right? The rate is 0.048, and we want to solve for T. How long does it take for it to double? Is that right? So we get 2 equals E 0.048T. Take the natural log on both sides. So then the doubling time should be the natural log of 2 over this. Let's see if that works. We said the natural log of 2 over the rate. It says round to 2 decimal places, so 14.44 years. We have 14.44 years. Let's close this out. Okay. And it wasn't too terribly bad. Let me check on you gentlemen in Zoom. I see the chat. Let me get the student real quick. Right here. Okay. And then let me let him in. Let me check the chat. Let's see. So somebody's requesting a group me. You see it there. All right, let's keep going. Okay. All right, so let's generate. Let's go to question 58. Right here. It says in 2011, a country's federal receipts, money taken in, totaled this 2.39 trillion. In 2013, the receipts were 2.85 trillion. Assume that the growth of the federal receipts F can be modeled by an exponential function and use 2011 as the base year, where t equals 0. Find the growth rate to 6 decimal places and write the exponential function for the total receipts in trillions of dollars. What does that tell us? It tells us like that's like scientific notation. Okay, I think I'm gonna take some notes on this one. I'm gonna start by getting a copy here. Okay. Let's see. Let's copy and delete. Let's hop over here. Let's give ourselves some space. Come on. Right there is good. Okay. Now it says it can be modeled. It says that by an exponential function. So let me see. I think we can, if we're doing like population growth. So let's try this model. So if we said the population based on time is going to be the initial p naught e to the kt, right? It's basically PERT. And then let's see what we're given. So in 2011, that's not 11, 2011, and we got to keep in mind that this is in trillions. And again, we can let this be t equal to 0 here. It was 2.39 trillion. We got to keep in mind that that's $1 trillion. All right. Okay. And then, so then what, 2 years later? So then in 2013, that's where t equals 2, 2 years later, it was 2.85 trillion. Okay. So we have two pieces of information. Modeled by an exponential function. Okay. 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 All right. So let's fit this data to that model. Let's see. So if we let 2011 be year 0, so then that means it's our initial population. Yeah. So that means, so from the first piece of information, if we let 2011 be year 0, then that means that P naught equals the 2.39, right? So then if we take that and couple it with the second piece of information, I think the only thing we don't know is the rate. We think we're trying to solve for the growth rate. So then we'll take the 2.39 times E. We're trying to solve for K. The time has been 2 years, so 2 times K. And in that year, the result, wait a minute, 2.39, 2 years later. And then that should equal 2.85, right? At this point, we have one equation, one unknown we can solve, right? So then if we divide both sides by that 2.39, we get this equals 2.85 over 2.39, okay? Take the natural log on both sides. Natural log of this. I'm just keeping it exact until the end. If I crunch those numbers and if I round early, it's going to throw off my final answer. If I do crunch the numbers intermediately, like as I go along, I need to write out that long decimal. And then we divide both sides by 2. K is going to be 2.85 over 2.39. Natural log of that, all divided by 2. Okay. So that should be the K, and that's an exact result, and then we can use that in our calculator. So now we're ready for the calculator. This one? Yeah. Where did, let me see. Full screen. There we go. That's exactly the one with that one. So clear. We got the natural log of 2.85. Yeah, 2.85 divided by 2.39, and then divided by 2. Okay. So back here. Hit enter. All right. Do not round it to the final, so then round to 6 decimal places as needed. 088013. 088013. 088013. Let's see. 088013. Okay. All right. I feel like there should be questions. Let me check with you guys in Zoom. We're not done with this one. I just want to make sure there's nobody in my waiting room. The chat looks good. Okay, guys. Let's keep going. Not there. Okay. So then part B. Come on. Thank you. Okay. Total federal receipts in 2015. Okay. So now we have an expression for K. So we have a model. So we want to, if it's 2015, let me see. That's what, 4 years later? So in our model, we want to evaluate it when T is 4. Okay. So let me write out our model. So the federal receipts based on what? Time. The starting amount. Come on. So P naught was 2.39. 2.39 trillion. E to the, I'm just going to reference this instead of writing it. K times T. So I'm going to say star times T. All right. When I do my calculation, I'm trying to keep K exact, you know. And so, and then we want to evaluate, I think we said 4 years later. All right, so we're going to put this into our function and then evaluate it when T is 4, right? Okay. So here, let me clear these out. We're going to say 2.39 times E right here. Now our K, I'm going to put that exact result. I'll do X times, X is our time. Let's see, the natural log 2.85 divided by 2.39. I got to get my grouping symbols proper here, and then that divided by 2, and I think this is fine. Okay. So then we're going to evaluate this function when T is basically 4 years later. Okay. And so that's trillions of dollars. I'll write the function. Okay, I think we got it here. Okay, I think we can use this. And we're going to use that rounded K. That might get a little bit. Now, I'm not sure if they want the 6 digits or 2 digits for this part here. We might get a little bit of kickback here. Okay, so it should be 2 point. Oh, come on, you're really not gonna let me see. Okay, I know what I can do. Let's go like this. All right, there we go. Now it should work. Let's get rid of this. All right. Let's go like this. Damn, it keeps resetting. Okay, I gotta zoom out. Now let's try it. Okay, that's gonna have to work. I know it's small, but that's the only way I can get it to work and like display properly so I can see it. So we said 2.39 times E to the power of, I don't think they really want us to write. I'm not sure if they want us to do 2 digits or 6 digits. I'm gonna use the 6 digits. Let me see. 0880 times t. Okay, and that's essentially what I have in the calculator. Let's try that. Okay, that's fine. So then that was our model that we got using that K. So then in 2015, I think we got that result here. So that's 4 years later. It says, use the answer from part A to find this result, round to 2 decimal places as needed. So $3.4 trillion. Okay. Is that it? No. When will the federal receipts be 7 trillion? So we want to set our model equal to 7 and then solve for t. Right here. Right. So we're going to do 2.39 e 0.088013 times t. Let's see. And we want to set that equal to 7 and solve for t. Okay. So if we divide by 2.39, 0.088013 t, 7 over 2.39. Take the natural log on both sides. 7 over 2.39. So then ultimately t is going to be equal to natural log of that divided by that decimal. 0880 13t. Okay. All right. Let me go ahead and crunch this. Let me see. I want this one. Okay. So then it should be the natural log of 7 over 2.39 divided by that rate that we found. Okay. We get this result. It says round to 1 decimal place. So 12.2 years after 2011. 12.2. All right. All right. I feel like there should be questions, but I'm just going to go with it. Let me check on you guys in Zoom. The chat looks good, and my waiting room looks good. Okay, let's keep going. All right. Let's generate. Let's go to question 46. I'll minimize the calculator for now. Let's go to question 46. Right here. Okay. Okay. So I'll zoom in some. Get that. That's fine. We'll go with it. So we're taking the derivative of a natural log. The way I like to remember the derivative of natural log is going to be du over u. So it's the derivative of the inside part over the inside part. Right? That's just remember. Derivative of natural log. How are you doing that thing? I need that window like this and come back. Yeah, this thing is so temperamental. I'm working on an iPad, and I don't think this software is really designed for an iPad, but I figured out just how to get around or how to do the things I've been trying to do. It's really weird, but it does work. Okay, so we're doing du over u. So the derivative of the inside part looks like it's going to be 8. Let's do a fraction. It's going to be 8x minus 7 over that 4x squared bit. 4x squared minus 7x plus 3. Okay. All right. Okay, let's do another question. And stop me if anything is not clear. Let's go to question 94. If you don't stop me, I will just go. I'm trying to get questions in, as many questions as I can in the time that we have allotted. So that's why I kind of keep the rhythm going. I find the derivative. So the derivative of exponential, the derivative of e is itself, but then when the base is not e, you got to say the derivative is going to be itself times the derivative of the power times the natural log of the base, right? So we got to, because the base is an e, we have to tack on that additional part times the natural log of the base, right? So when we go to find its derivative, first it's itself. So it's going to be 700, 1.679 to the power of t. The derivative of the power is just going to be 1. And then we're going to say times the natural log of that base, 1.679. Okay, that should be it. Because again, if this were base e and we multiply by the natural log of e, well, the natural log and e cancel, or it's just 1. So that's why initially we didn't see it. But then when the base is not e, this is how we address it or account for it. Okay. All right, let's do another one. Generate. Let's go to question 40. When I was in high school, my math professor or teacher, I guess in high school, he was from Nigeria. His name was Mr. Lagunju. And he'll be at the board, like for instance, this question is question 40. He'll be like, okay, today class, we're working on question 40, like part 1 of foul. It's like, and like nobody would like flinch or smile or anything. I was like, am I hearing this right? Am I the only one hearing him say it like this? And it always like caught me. I was like, why is he saying 4 like that? It's kind of like how Stewie would say like hoop whip. And like Brian was like, why are you saying it like that? You know what? I'm just talking about some cool whip. That's what it was like. It was so surreal. It was kind of funny. All right, so that was enough of a little bit of a tangent. Let's see. You plan to invest in an account which pays 4.5% compounded continuously, so that's PERT. If the investment period is 6 years, then the future amount is given, right? Gives a total balance of P dollars. Let me see. Future amount, okay, that's fine. Find a formula for A prime of P, okay. Yeah, let's just take the derivative, right? Let's do it. We can do it here. So the derivative of E is itself. Let me see. P, E, wait a minute. Mm-hmm. Okay. Oh, we're taking a, okay, wait a minute. So here, this was a little bit different, right? Because at first I was going to just take the derivative of E. Like normally we take the derivative with respect to X, right? And usually the X is in the power or the exponent, but it's not actually there. We're not taking the derivative with respect to X here. We're taking the derivative with respect to P. So we got to treat P like a variable. So if P is our variable, this E to the 0.27, that's just some random number, right? So it's really just a number times X, right? So then the derivative of a number times X is just that number, right? So we don't need the P. So E to the power of 0.27. So let's get rid of the P. And I think this is it. Because it's just some number times X. So then the derivative should be just that number. Okay, let's go with this. Okay. And they almost got me with the okie doke. I was just cruising along. I was like, wait a minute, something looks off, right? So then round to the nearest cent. The rate of change, it should just be that number because there's no P there. So we can just evaluate that number. It doesn't matter what P is because in our derivative, there's no P, then it's whatever that decimal is. Let me pull up my calculator. Okay, so all we're gonna do I have like multiple windows open or something? No. Okay. We're just gonna evaluate e to the power of 0.27. E to the power of 0.27 to the nearest cent. Rate of change. Let's see. Total amount in P dollars. Rate of change of the dollars is $1.31. Is it? Let me see. $1.31. Is it dollars per year? Let me see what my options are here. Dollars increase. Years per dollar? No, it's dollars. Total amount per yearly increase. Dollars increase in the total amount per dollar increase is not the first one. It should be this one. And we got 1.31. Let's try that. 1.31. Come on. 1 point. Nope. Nope. What did I hit? 1.31. Let me see. Dollars increase in the amount per yearly increase in the investment period of time. Okay. I think that's okay. Wait a minute. Wait, let me think about this one more time before I submit it. Per actually, because the dollar increase in the total amount per dollar increase in the initial investment. Actually, I think it's the first one now because the P is based on dollars, right? We're doing the rate of change. Yeah, actually, I think it's the first one. Let's go with this one, actually. Yeah, this one is weird. It's weird because we're used to doing these in terms of time, and we have to like this isn't in terms of times. Like, let me see. We're doing the future amount based on the initial amount instead of based on time, right? So that's why I don't know how I caught that. I guess I got some rest today. I know I was like way more choppy on Monday, and I guess I got some rest, some good rest today before class. I ain't gonna lie, I've been gaming for like 4 or 5 days straight, like every waking moment. I'm so behind in my work. But I did get some rest. Like I eventually put it down. I finally got a breakthrough and I kind of figured out this character I was working. And I was testing out my latest build. Man, the game is so much fun. I be feeling like Iron Man, like how he does different iterations of his suits. Like that's how the game is. You can build like the customization level. That the number is so big because it's at least like 50 characters. Each character has an option of like 6 or 7 different roles. I mean, it's like I can't even begin to list out all the options so I can begin to count it. That's how many different combinations you could do. You can pick any character, build them like a tank, marksman, mage, fighter, assassin, support, right? So those 6 options, you know, it's some astronomical number of the different combinations that you could do. And so that's why I like it because it's so dynamic. You know, every time you don't really get bored, right? But I do get obsessed with it sometimes. So, well, oftentimes. All right. The rate of change. Let's see. dy with x. So the rate of change of the future amount based on the initial investment. I'm gonna see a future value of. Let me see. This is the rate of change of the future amount given that the initial investment is $6,000. Let me see. The future value of a 6-year investment of, let me see, the future value of a 6-year investment, is it 6 years? Uh-huh. The future value of a 6-year investment of $6,000 is 4.5%. Oh, I got to think about this one. Why would it be 7? I feel like it's either A or B. Are there some other options? No. But let me see. The future value of a 6-year investment of $6,001 will be blank more than the future value of 6-year investment at 6,000. I think it's A. Yeah, because we're not really talking about a 7-year investment because it says 6 years. So that's why I ruled out C and D. I ruled out B because it has the wrong rate. It says 5.5%. It looks like it's supposed to be 4.5%. Okay. And then I think that the result here should just be 1.31 more than the future value. Like, so how much does it increase by, like, in the next year? That's the rate of change. All right. Or the next, not year. Again, I'm still thinking in terms of time. Let's go with 1.31 here. Let's see what happens. Yeah, that's kooky. Okay. Right. Okay. So then with this part C, we plug in the 6,001 into the original, into that PE to the 0.27. We just plug those two results in. We just subtract, right? So for instance, let me see if I go to my y equals, I'm going to clear this out and I'm going to put x times e to the power of 0.27, okay? And then I want to evaluate this when P is what, 6,001 minus, nope, I need to close that off, minus evaluate it when P is 6,000. All right, so we're getting an actual change from 1 year to the next. Okay. To the nearest cents, so 1.31. Got the same thing. Ooh, it's making me a little nervous. Let's go 1.31. Wait a minute. Dollars per year. Let's just try it. Let's see what happens. Okay. All right. Let's do another one. Generate. What's the time? We got time for a few more. It just depends on how long these take. Let's go to question 28. Right here. Okay, so it looks like we have these product rule along with like power rule and exponential rule, right? So the product rule goes what, the first times the derivative of the second plus the second times the derivative of the first, right? So we should be able to do this here. I'm going to zoom in just a little bit to make it a little bit bigger. Let me like this. All right, so the first is this guy, x to the 9. The derivative of the second, the derivative of e is itself, times the derivative of the power. I mean, yeah, it's just going to be 10, okay? So that's the first times the derivative of the second. And then we're going to say plus the second, which is this, times the derivative of the first. The derivative of the first is 9x to the 8. Okay. I mean, we could factor it. I'm going to see if it takes this. Okay. Again, all I did was the first times the derivative of the second plus the second times the derivative of the first. Okay, let's see another question. Well, I'll probably stop. Well, we got a solid 20 minutes. Let's try to go for 20 minutes. It's not necessary. Let's go to question 39. Okay, let's see what's going on in 39. Let's zoom out some right here. So it says this equation gives the balance after 2 years of an initial investment of $2,000, which pays 5% compounded continuously. Find the formula for the rate of change of A with respect to time. Okay, so take the derivative. The derivative of E is itself times the derivative of power. Okay. Okay. So then if we said, again, the derivative of E is itself times the derivative of the power. So that's going to be 2000 E to the power of 0.05 T. And we got to say times the derivative of the power is just going to be 0.05. And then 0.05 times 2000. Let me see. 10% would be what, 200? So then half of that would be 100. So I think if we multiply those, we should get 100. It would be a 10 and 0.1, 1, 2, 3, 100 sounds good, yeah. So I think this becomes 100. Okay, I think that's okay. Okay. So then if we evaluate that when T is 10, okay, so we'll use a calculator. We're going to say 100, come on, E, yeah, E to the power of 0.05 times 10, 0.05 times 10. Okay, round to the nearest dollar, the rate of change. Round up to the nearest dollar. So $165. $165 per year. Dollars increasing amount per yearly increase in investment. Years per dollar? No. Dollar increase in the total amount of dollars per increase in the initial investment. It's not that one either. It should be this first one. The dollar increase per year. Okay, at 10 years. That's that's the rate of change of the dollars per year at 10 years. Okay. Let me zoom out some so we can see this a little bit better. It says compare the approximation of 165 to the actual. Report your answers to decimal places. Let me see. Okay, interpret A prime of 10. Let me see the future value. Is it 10 years? Yeah, 10 years. The future value of a 10-year investment of $2,000 at, is it 6%? It's 5%, so it can't be B. It's not A because it's not. We're not talking about 11 years, so it should be C. Future value of a 10-year investment of $2,001 will be blank, will be $165 more than the future value of an investment of $2,000. Okay. So we're going to go C, and that result's going to be 165. Investment will be, let me see, a future value of a 10-year investment of $2,001 will be $165 more than a future value of a 10-year investment at $2,000. Let me see. 6%? Is that 6%? Doesn't sound right to me. 11 years per year? Maybe it's one of these. The future value of an 11-year investment of $2,000 will be $165 more than the 10-year. Okay, let's go with A and make that one 165. So basically, they're saying like 1 year past the 10-year mark, you know, we'll make an additional. It'll be worth $165 more. So then, if we say A of 11 minus A of 10, so then we just put 11 into the original, put 10 into the original, and subtract the difference, subtract those results. So I think we can do that here. I'm going to clear this out. I'm going to put 2,000. This is probably going to be the last one because I got to get going. e to the power of 0. That's fine, 0.05 times t. Okay, 2000 e. Okay, that looks good. Let's close this off. And I think we kind of did one that was similar and just changed that to 11 and 10. So this one needs to be 11. And this one over here needs to be 10. Okay, round to 2 decimal places as needed. 169.06. Right here. 169.06. Okay. All right, gentlemen. Are there any burning questions before we go our separate ways? All right, so I mean, this one went a lot more smooth than it did on Monday. That's why doing limited attempts. If you're just stuck, don't hesitate to screenshot it and reach out to me. Just do what you need to do to get through it. If there aren't any other burning questions, we're going to go ahead and end the session here. And from one beautiful mind to another, have a great weekend, gentlemen. Take care. Again, your exam 1 is available, and we'll start chapter 3 on a Monday. All right, gentlemen. Have a great weekend. Take care. Peace.